Hello folks, this is Tom from anti-proton.com. When measuring a gamma spectrum, when you're looking to see whether or not it contains something radioactive like this, sometimes this is very easy, especially when you have something that is reasonably radioactive and you can easily tell. But what happens when the background, which is just normal, random, cosmic flux and all that sort of stuff, what happens when the peak you see is very close to that background? How can you determine statistically if it's actually real or not? Well, I'm not an expert of that, not by any means. In fact, far from an expert. I'm a lay person, aka an amateur. So, this is the method that I use, and I'm going to explain the method and how I derive the method. And pretty much this is kind of open for comments. I would like people to look at this and say, hey, that's great. I am an expert and I know that you're doing it right. Or, hey, that's completely wrong. I've done this for years and this is not how you do it. That sort of thing. So constructive criticism is what I'm looking for. Let me start by saying I did not invent this method myself. I'm not taking credit for doing it. This is actually based on several methods that are used by scientists. In fact, if you are a scientist, you'll probably recognize what I'm doing. I spent a huge amount of time doing this and working on it, trying to figure it out, probably more than I needed to. I was facilitated by this, one of the greatest books ever made. This is from Gordon Gilmore, aka Dr. Gilmore. And Dr. Gilmore's gamma ray spectrometry, this says, you can't probably read it very well, but it says Practical Gamma Ray Spectrometry, second edition. This is like the greatest book ever. And I'd go all the way through it and everything, but I think it kind of violates copyrights for me to open it up and go page by page, because you're supposed to buy the book to see what's in it. But I got the method. I will show you the one page where I got the method. I got the method from here on page, let's see, what page number is this? Page 116 details how to do exactly what I'm about to show you today and all of my various notes on how to do it. Also, of course, I keep myself refreshed with my manga. Yeah, I know it's pronounced manga, so excuse me, but I like calling it manga. It sounds to me better than manga. I don't care if it's right or wrong. My manga guide to calculus, manga guide to statistics, and this linear algebra one too. So I recommend those because they're awesome, super fun too. And of course I keep myself excited and spurred on with books like this 1951 Prospecting for Uranium book from the United States Department of Atomic Energy. Yay! For like $3 on eBay. Now, let's get down to the actual important part, the actual math. So here we go. We have channels in a spectrum, and we have the counts per channel. So channel, count. So as you can see when you look at this, there's kind of a peak right here, right? See this whole peak? Now we're looking at this with our own two eyes, and we see there's a peak here. Okay, no problem. Of course, it doesn't have to be like a photo peak from an actual nuclide. It can actually be various types of artifacts, Compton edges, backscatter peaks, sum peaks, escape peaks, all kinds of things. But let's say we're looking at this, we kind of break this off and we say, look, this is our region of interest right here. In between this line and in between this line, this area is our region of interest. We can assume that somewhere in here there's a background, and somewhere above this background is the peak. The question is, how much of this is statistically important? There's lots more math required to determine the actual activity and stuff. But before I can even do that, I have to first know how much I'm working with. So how do I figure that out? Well, I have some background on either side to kind of approximate where the background would have been, and then extrapolate from here where the peak is. And I'm about to show you the mathematical method that I actually do for, or not do, but use for doing that. So let's get on the computer and take a peek at that. Alright, when you're looking at a spectrum, you have, of course, your background, and then you have both valid peaks, and you have various artifacts. Well, determining whether or not you have a backscatter peak like this, or an actual cesium-134 peak like this, that has little to do with this. What I'm talking about right now is determining how much of, let's say, this peak right here, this cesium-134 peak, how much of this is actually really validly the peak, and how much of it is the background. And the statistical method of figuring that out. See, if we select this area here, how much of this area here, that's 451,543 counts, how much of this is from the actual nuclide and how much of it's just from background. And it should be determinable using, well, basically math. So let's kind of look at how I am doing that, and this is based off of Dr. Gilmore's method, but it is not exactly the same. I've made some tweaks and modifications. And this is where everybody can look and say, hey, that's not right, or hey, that's great. So anyway, let's look at his peak that's a little harder to figure out. Take the peaks in this tuna sample I took up. Well, I sampled. I wasn't really doing it for food safety or anything. I was just doing it for giggles. But this is tuna. And you can see a peak here, and like I said, these may or may not be valid peaks. They could be other things too. But obviously there is some formation coming out here, here, and here. Now obviously you can tell that this little bit of a rise right here is actually the Compton Edge, or it's Compton Edge and Compton Plateau from that right there. But anyway, the point I'm trying to get to is what's what statistically. So let's take a look at this. This ROI that I just picked up, and normally I use a little more care when I actually select an ROI. I just kind of did that fast and ghetto style. This is potassium 40. How would we determine how much of this was a valid detection and how much of it wasn't? And if we had an ROI over here that we expected to be a particular nuclide, let's say we ran the test ahead of time and found a peak perfectly for this particular nuclide, and now I've run this test for the same exact ROI and everything stayed the same. How do I know if this is above background? How do I figure that out? Well, I pretty much have to look at the background on either side of it and kind of guess where everything was going and see how much extra I had. So let's look at how that works. This is a pretend spectrum I made. It's not real. Obviously, if you look carefully, you can see that there's a peak right here forming in this little pretend spectrum I made. But let me show you kind of how I'm looking at this. You have the channels, just like in your detector at the bottom, and you have counts going up and down. We have 0 to the maximum of, like, what, 28, 29 counts, somewhere in there. What I did was I broke off the sample region of interest, ROI, region of interest. That's this part right here. This is the actual place that I highlighted and said that this is the sample. If we were to go back, that's this, the blue or the green part. And then I created a background here, which I'll call background P, and background over here, which I call background Q. I just gave them those P and Q because those are easy to remember, and they should be lowercase, and I made them uppercase. Oh well, good for me. But basically, if we were to pick this out, this would be, P would be like right here, and Q would be like right there. You get the idea. Basically adjacent to the ROI. Now, that's similar to how the software does it, by the way. Looking back, I take the mean of each of these two backgrounds. See, here's the mean of P, and I kind of did this manually. I'll show you the actual mathematical equivalent of it in a minute. The mean of P, that sounds funny. And I took the mean of Q, and they may not actually be equivalent. That's why I draw the line down here across them at an angle, not just because of the fact that in this case they aren't, but also to illustrate in any case that they may not be. This line is supposed to represent the approximate, the derived, if you like, mean of where the sample ROI's background should be. In other words, if this sample were never here and this were just background following along the scope of the rest of this background, I would expect that its mean would be somewhere down this lane right here. And in my original math, I used linear, just a linear connection between the two of these. I later switched to an integral, not only because it takes into account the bottom part here, which I'm trying to grab a hold of to figure out how much actual background there is, but also because then I can, put some quadratic math and stuff into it here if I had some crazy multi-data pointed background going on. But anyway, for the most part, I'm using just simple lines for this. So we cannot say, of course, that all of this above the line is detected. That's not reasonable because we know that there's some, we'll call it fuzziness right around here. And by what I mean by fuzziness is I mean that we can be confident at the farther and farther that we move away from the mean, we can be more and more confident that we have a valid detection to some degree. And we can turn that into something mathematical and quantifiable as opposed to just simply categorical. Now let's move over here one more step and kind of figure this out. See this line right here? This is some level of confidence that I'll show you mathematically how I come up with it. Some level, whatever it might be, and everything above it is to a particular degree considered a detection, not a specific activity, nothing like that. I'm not saying that this is X number of becquerels per kilogram or something. That takes a lot more math and takes a lot more geometry, figuring out where everything is and all that stuff. That's step 2. This is step 1. How many counts can we be reasonable in assuming are statistically valid? Dr. Gilmore calls this the critical limit. And so what we have is the standard deviation multiplied by some z-score, if you like, or something to that effect, to figure out exactly what this should be. So let's look at the math now and see what we are using. This is the basic equation for doing it that I use. And I didn't really step too far beyond what Dr. Gilmore does, I don't think. I added a few parts in here, but here's what I do. I take the ROI. Let me jump back and forth a few times. Here's the ROI sum. What is that? That is this whole area. This is the ROI, the region of interest sum. That's everything that exists. Okay? I take all of that and I'm subtracting from it all of this to equal detected counts. And what is all of this? Well, simplistically, what I'm doing is I'm taking 1.645, which is a one-tailed 95% confidence. One-tailed in this case, because I'm not worrying about going below, I'm worried about going above. If I were worrying about going below, I would take a two-tailed, but I'm going to do a one-tailed confidence of 95%, meaning that that 95% of the time, anything above what we detect here is going to be a count. Anything below will be not a count. So I'm taking this confidence and I'm multiplying it by the square root. And this is where it gets crazy here. Basically, this is the square root of 2 times the background. That's the basic equation which this is derived from. 2 times the background. Now, the reality is we go a little farther beyond there. What we do is we calculate that line. See this whole integral right here? This integral that you see right here, and let me jump back to it, is this. This integral right here that you see is this. The color codings don't match up, so ignore that. But this whole integral across here is this integral right here. It's a very simple integral. I'm just simply saying take the change in the from P to Q, the change between these guys, so this minus this, divided across this in the number of channels that I have. And that's basically a linear derivative is what it boils down to. It's kind of a ghetto way of coming up with it, but it's pretty simple. And then I just take its integral across. So you'll end up with this multiplied by the integral of x plus this multiplied by the integral of 1 dx. Anyway, so when you're done with this, you come up with this area underneath. That's that. And then I'm using this relation right here, 1 minus the total number of n. Let's see, n is this, the total number of channels. And I'm dividing that by the width of the 2 backgrounds, which in Dr. Gilmore's book is 2 times m. In his case, m is the width of the background. But for me, I'm actually using the widths added together. And the reason for that is because you never know when you might actually have different widths. And what I mean by this is that if this is the mean, see this mean right here? Let's go back again. This is the mean. See this blue line? This is the mean right here, okay? That's this mean right here. Remember, the colors don't match up. That's the mean. I'm saying that the standard deviation multiplied by that number right there, so it jumps up. Anything above that is detected. Now, let's do this in math and see if it comes out right. And it's not going to come out right. It should, but it should come out similarly to where it needs to be. Get away from there. All right, this is the original precursor math that I did the first time, and I won't go through all this crazy math on the side, but I wanted to show you the gist of what I was doing. I was taking the actual backgrounds right here, and I was actually putting in the data to see. I mean, I actually typed the data in by hand. I invented this. None of this existed. I statistically created it, and I simply said, I know because I made this model that these little counts right here are the actual real counts, and these are not. That's the nice thing about making a model. I can actually make the data what I want it to, as opposed to doing experimental tests. And what I boiled down to when I came up with this was the actual background was 58. The calculated background was 60.75, pretty close. The actual number of counts was 36. The oh, where was it? Somewhere around here I have the counts that I detected. The net ROI was 33, so pretty darn close. This evolved into the next thing that I did. Let me show you the next thing, and this is the final thing, and that's this. This is another sample I made that doesn't exist. I invented this as a model for testing purposes. Here it is. It consists of a total of um, 40 channels, see 40 channels, of which these red ones here are the actual region of interest, and these blue ones here are the P and Q, if you like, the backgrounds and the sides. And I figured out P's information, the sum of the P, that's how many counts are in it, P bar in this case, which is the average of P, which is 13.4, the width, which is 10 channels wide, the start, the end. I did the exact same thing for Q over here, so I have all the information for Q. Most importantly, I have P bar and Q bar, which are P bar is the mean for P, Q bar is the mean for Q. I have N, which is the number of counts going all, not counts, excuse me, the number of channels going all the way across the bottom. I have A and B. This is A, this is B. It's the sort of start and beginning points of the region of interest. The total gross for the region of interest only. And pretty much I took the derivative here. Let's see, 0.375 negative 0.375. That basically is the mean for Q minus the mean for P divided by the number of channels. So how much this moves as how much this changes and distributed across the actual channels. If you get the idea, it's the line here. And then I estimated that with using just a simple integral. Came up to 176.931. This is how many counts I would expect in my background from the bottom to the mean anyway. Right here, just the bottom to the mean. That's how many counts should be in there. Now this number will not be equal to the real background, and the reason for that is because it's to the mean, and the mean is not actually where the real background ends. As you can see over here with P, for example, the mean's somewhere right around here, but there are counts above it. But it will be used to derive it. So that's the estimated background to the mean. My 95% one-tailed confidence, as you can see, is 2 times the background. So let's look at this for a second. The background is G22. There's 22, there's G. So you see this is the 186.913. And so I did whatever that number was, 1.645, I think it is, times the square root of 2 times the background, which works out to be 2.33 times the square root of the background. So there it is. That comes out with that number, which is 31 point something. And I calculated my critical limit, and I did this whole bit right here is basically the math that you saw here, except minus the integral. This whole integral piece right here from the blue line to the blue line gets replaced with a big old B for background. And as you can see, that's what I did right here. This, you might have to kind of trust me, but this piece right here is just this math right here. Well, yeah, so just kind of maybe bear with me here. My little trust might have to go into that. And then simply what I said was the region of interest, that's this whole area here, minus the predicted background, 186 point whatever, plus the critical limit, the two of them put together, equals this right here. So my assumption is that there are 306.47 blah 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 blah, a whole bunch of numbers, 306.47 counts within this area that are not part of the background, that are the detected peak. Okay, that's what I've come up with. So I believe that I have 306 detections. Now, that does not take into account things like the efficiency of the probe and all that other stuff. You know, all that has to be accounted for. So please don't bring that up, because yes, I know that has to be accounted for. But this is the base thing. Before I go any further, this is the base piece of information to know. I could toss the other stuff in as a few derivatives partially through there and integrate them, which is another reason I use the integral. But anyway, now what I did was I took the sum of the region of interest and I subtracted from it what I believe to be the detected counts, and the remainder is what the actual background should be above the mean, taking into account the counts that go above the mean. So what we end up with is this, just to show you. This is how much, and I'll highlight it. This is how much, and I'll show you do the revealing in a second. That's how much that's how much I think I've counted. This is how much is actually there. And this, which will make kind of a soft blue color, this is what I believe the background to be. Now let's see what the real actual data was, because I told you I have the real data in here. So show. Okay, I took the real background that has been mathematically derived to be approximately flowing along this line right here. This is the real background. This is the background that would have existed had no counts been there, plus the counts that I added from my pretend nuclide. And what it boils down to is, drum roll, the real background should have been 229 counts. I thought the background was 210. Not very far off. Far off, yes, but not completely far off. I could have increased this from 95% confidence to a 99% confidence and jacked that up really high, and then that probably would have been even more accurate. So pretty close, right? Not too far off. And my total counts, my real actual counts, you would never ever know this in the real world. There's no way you would ever know this. And only if you make a model that's not real would you know this. There's 288 photons detected out of 306. Off, yes, but not very off. Now, I think I could refine this a little bit, and I think if I boost the confidence up from 95% to like 99%, something like that, 98, 99, somewhere in there, I think that would probably make me more accurate. But do you see how this works? I'm thinking that I may have something here. I think that this is working right. And when I say have something, I'm not doing anything amazing or new. This isn't a discovery. The only thing I'm affirming is that, hey, I might actually be doing it right. So as lame as that may sound. So if anybody has any questions, please let me know. Comments, whatever. Here's a earlier attempt to do it with the potassium I was looking at earlier. My score didn't come out too far off of where the Spectrum Techniques score came off of, because they use the same sort of method themselves. So this is based on Dr. Gilmore's with a little bit of Tom additional information tossed into it. Most importantly, this. I throw the integral in, which I find to be very useful, because later on when I'm adding efficiencies and stuff, I can toss those right into this part of the equation and integrate them all the way across without any problem. But, you know, that's just me. I like doing that. So that's that, and that's that. And that's what I figured out. Let me know what you think, and if you don't like it, tough nuggets. This has been Tom from anti-proton.com, and thank you for watching.